Okay, so let's start. Okay, so let's start. So in the last lecture, we were looking at this procedure mark, right? So what was this mark procedure doing? So essentially, it was trying to find those states pairwise which are distinguishable, right? So if you recall, so we considered the states, for example, you consider, let's say, Q2 and Q3. So these are, Q2 is a final state, Q3 is a non-final state. So they can be distinguished by this string epsilon, right? And then we could see that if you consider the string 0, then again, like these states, let's say Q3 and Q0, they can be distinguished and so on, right? Because what happens, like from Q0 on 0, you could go to Q1. From Q3 on 0, you could go to Q2. And Q2 and Q1 were already marked because they are distinguished by epsilon, right? So this is what the marking procedure was doing. And then after 0, you can mark with 1 and with 0, 1, and so on and so forth, until finally you see that no more pair of states are going to be distinguished, right? So this is what the mark procedure was doing. So if we look at it carefully, so this is what. So first we remove all the states which are inaccessible from Q0. Then the base case is like P and Q are distinguishable if P belongs to F and Q does not belong to F. So essentially this is like saying that P and Q are distinguishable by epsilon. Okay. And then we had an iterative step, which is like if from P, if on A, you can go to P prime, from Q on A, you can go to Q prime, and for some A. And it happens that P prime and Q prime have already been shown to be distinguishable. So that means the pair P prime Q prime is marked. Then we mark PQ as distinguishable, right? Repeat the iterative step until no previously unmarked pairs are marked. Clear? Right? And then we had this, like we had a marked flag, which is we set to true, and then we set it to false. Then if you again mark a pair, then you set it to true. And so if you do not mark any pair, then the marked flag will be set to false, and then you come out of this loop. Right? So any new pair, if you are not marking any new pair, then it will remain set to false, and then the loop terminates. Correct? So can you say, like, why is it the case? So do you think that this mark procedure will always terminate? Or do you think that there can be a case in which the mark procedure is not going to terminate? New state has to be marked. Yes. New pair of states has to be marked. Right. Right. Correct. So it should terminate, right? Because so you have only a finite number of pairs. First of all, you have only a finite number of pairs of states. And then in every iteration, if a new pair is not found to be marked, then you come out of the loop and this procedure terminates. Clear? So this mark procedure always terminates. So this much we can say, right? And then the next thing, so what is the objective of this mark procedure? What are we trying to do? We are trying to minimize the DFA. And in the process, what are we getting? We are having only those pairs of states which are not distinguishable by any string. So they are indistinguishable. And then we are saying that we would club them. together. So at the end, what you get is essentially the classes corresponding to the indistinguishability relation. Excuse me. Okay. So is it clear? Right. Good. So let's look at the correctness of the mark procedure formally. So what are we saying? The procedure mark applies to any input DFA. If you are given an input DFA like this one, here is an input DFA. So the procedure mark applied to any input DFA terminates and determines exactly all pairs of distinguishable steps. So whatever pair, so we started with a table like this. So whatever pair remains so whatever pair remains unmarked, right? So what are they? They are indistinguishable. They are indistinguishable. And whatever pair you are marking, they are distinguished by some string, right? So this is what we saw. And now, in order to prove the correctness of this theorem, that indeed this mark procedure, it determines exactly all pairs of distinguishable states. So we need to prove the soundness and the completeness of this procedure. So what does soundness mean? Soundness essentially means that if it marks a pair of states, then they are indeed distinguishable. And completeness means that every pair of distinguishable states can be marked by this mark procedure, right? So let's look at the completeness first. So we discussed this, and hence I'm going a bit faster, like we discussed this in the last lecture, the broad ideas. So what is the idea of completeness again? So if there is a pair of states which is distinguishable, then the mark procedure is going to actually mark them as distinguishable, right? So suppose there is a pair of states which are distinguishable, then there exists a string. So what is the definition of distinguishable? There exists a string X, okay, and there can exist multiple such strings, but you can consider that string which is of one string which is of minimal length, which distinguishes the pair of states, right? And what we say, we are going to prove the completeness by induction on the length of this minimum possible string which distinguishes this pair of states. Clear? So there exists a string X of minimal length which distinguishes this pair of states P and Q. And so suppose you consider the base case where X is epsilon. So essentially it means that the length of X is 0, and all entries which are distinguished by epsilon, they are marked, right? In the beginning, all the entries. So we are proving completeness. So if there exists a pair of states which are distinguishable, then there exists a string of minimal length which distinguishes them, and we are proving the completeness by induction on the length of the string. Okay, so you consider pairs of states which can be distinguished by epsilon, right? All such states are indeed, all such pairs of states are indeed marked, right? Because why? Because such a state, like one will be final, one will be non-final. And indeed, our algorithm, the mark procedure indeed does that, correct? And then you can think of the inductive case. So suppose the hypothesis is true for, suppose hypothesis is true for X less than M. So what does it mean? It essentially means that all pairs of states P comma Q, which can be distinguished by a string of length less than M, strictly less than M, they have already been marked. So this is my induction hypothesis, right? And now you consider, suppose x, the length of x equal to m. So this is the minimum length which is going to distinguish, minimum length string which is going to distinguish a pair of states p and q. And you say that let x equal to ay, and hence y is of the length m minus 1, right? Now, so x is going to distinguish p and q. So there is some pair of states pq which can be distinguished by this x, and x is of length m. And then we are going to say that indeed the mark procedure is going to mark this pair p comma q. Clear? Okay. So now you can say that suppose from p on a you go to p prime, and q on a go to q prime. So this is a DFA, right? So we are doing a minimization of the DFA. We are marking pairs of states which are indistinguishable, which are in fact, indistinguishable by in a DFA. And so suppose this is the case. Now p prime, q prime are, by the induction hypothesis, they are already marked by y, right? And what does the mark procedure do? The mark procedure, if it finds that if it, by doing this A, by doing taking this action A, if you reach a pair of states which is already marked, then you mark p comma q. Hence mark p comma q. Right? So this kind of completes a inductive proof. Okay. And then we have to prove the soundness also. So what is the idea of soundness again? That if you are marking a pair of states p comma q, then they are indeed indistinguishable. If we are marking, if the mark procedure marks a pair of states p comma q, then they are indeed indistinguishable. So the idea is that, like, so we can think of like in the initial iteration. So at iteration 0, you are marking all pairs of states which are sorry. What did I say? So I said, if you are marking a pair of states p comma q, then they are distinguishable, right? If you are marking a pair of states, then they are distinguishable, correct? And in the case of soundness, we are saying that if the mark procedure indeed marks a pair of states, then they are indeed distinguishable. Okay. And in the case of completeness, if a pair of states p comma q, they are distinguishable, the mark procedure indeed marks them. Okay. So the mark procedure marks those pairs of states which are distinguishable. Right. So this is what. Okay. So in the soundness, what are we saying? So initially at iteration 0, it marks all those pairs of states which can be distinguished by epsilon, right? So initially it is marking all those pairs of states which are distinguished by epsilon. So if you recall, what does it do? It marks, so suppose if you have p comma q, it marks them if one of them belongs to the final state, the other one is not a final state, right? So then it will be marking them. So it marks all those pairs of states which are distinguished by epsilon. And then we can essentially, in the soundness proof, what we would need to show is that in iteration I, it would mark all those pairs of states which can be distinguished by strings of length I. Right? So if you are in fact in iteration I, if you are marking some pair of states, say in iteration I, if you are indeed marking a pair of states p comma q, then it means that there exists a string x such that the length of x is I and p and q are distinguished by x. Correct? So this is the soundness that indeed if the mark procedure marks a pair of states, then this pair of states are indeed distinguishable. Clear? Okay. So this is kind of the soundness idea. I mean, you can, like, we have seen similar things, so you should be able to kind of write this out formally. Okay. And now what we also discussed is that the mark procedure, what does it construct? It constructs an equivalence relation, which is the same as the indistinguishability relation with respect to L. Because if you consider any pair of states, if they are not marked, which means that they are indistinguishable with respect to any string. With respect to any string, they are indistinguishable. Because if there exists a string which distinguishes a pair of states, then that string is of finite length, right? And then the mark, since the mark procedure is sound and complete, right? It is going to mark those pair of states if had they been distinguishable. So if they don't get marked, which means that they are not distinguishable by any string, right? Hence, if you consider the equivalence classes of these states, which means that the set of states which are not marked and hence they are not distinguished by any string, this class essentially corresponds to the classes of this. The classes that you obtain after the mark procedure, they essentially correspond to the classes of the indistinguishability relation. Clear? Okay. Right. So now, so we just talked about the mark procedure. So we are yet to do the minimization. So what did we say in the minimization? So suppose we found that these are the pairs of states, right? These are the classes that you get, like Q0 and Q4. They are indistinguishable. Q0 and Q4 are indistinguishable. Similarly, Q1 and Q7 are indistinguishable. Q3 and Q5 are indistinguishable. If they are indistinguishable, we are going to form a class corresponding to each such indistinguishable set of states. And we are going to merge them. And what we get is an automaton which looks like this. So this you get by merging 0 and 4, by merging 1 and 7, this you get by merging 3 and 5, and so on. Okay. And now what we want to say is that this DFA, the resultant DFA that you get by this procedure of merging the states of a particular equivalence class, gives you a DFA which accepts the same language. Further, this is the minimal DFA accepting this language L. Okay, so now we are defining this procedure reduce. So what does it do? So given a DFA, we construct a reduced DFA M prime. So this is the input, this is the output. Now how do you, so what is the, what does this procedure do? So it will first call the mark procedure, which we saw, to obtain the set of equivalence classes. Right? It will obtain the set of equivalence classes, and the set of states in the new automaton is essentially is nothing but this set of equivalence classes that you have. And what is your set of final states? It's those equivalence classes such that a member state, a member such that Q belongs to F, where F is the set of final states of the DFA. Any question? You have a set of equivalence classes, right? Now there can be some states which can correspond to the set of final states, right? And there will be an equivalence class corresponding to some of those states, right? And you are saying that they form the new set of final states of this automaton that you are constructing. Clear? Now, if I ask you this question, is it the case that all the final states will be grouped together? Are they going to be there in the same equivalence class? May not be the case, right? So this we discussed, I think, sometime, right? That it's not necessary that all the final states here, have to be grouped as the same, as a single final state here. It's not necessary. Yeah, if that could have been possible, then every DFA could have been converted to a DFA with a single final state, which we saw is not always possible, right? Good. Okay, so now, so this DFA, so how, and okay, and let's also look at, so we did discuss this Q prime, we discussed this F prime, and now what is this delta prime? So delta prime, this equivalence class comma A, is the same as you can consider delta of QA, correct? And consider the equivalence class of that. So you apply delta of QA and consider the equivalence class here in order to define the transition relation here in the new automaton. Clear? Now the claim is that this DFA M prime that we have constructed, the DFA M prime that we have constructed by this procedure reduce with the inaccessible states removed. So what is the inaccessible state? Which you cannot reach from Q0, from the initial state, okay? Or the equivalence class of Q0. So this is the minimum state DFA for its language. So this is the main theorem. We did this entire exercise, this algorithm, and what we are saying is that the resultant DFA that you get as an output of this procedure is indeed the minimal DFA accepting the same language. So first, we need to show that this indeed accepts the same language. So how are you going to do this? How are you going to do this? So what we want to prove is that L of M prime is indeed L of M. How are you going to prove this? So here, this side, right, we saw similar when we looked at the translation from NFA to DFA subset construction. So we looked at it's very similar kind of approach. So we always use this delta star function, right? So here it is a delta prime star. And so what is the initial state? You have Q0. And then you consider an X. What do we need to show? So suppose I would call it a lemma, which you can prove by induction on the length of the X. So what is this going to be? Very good. So it is going to be delta star Q0X and the equivalence class of this, right? So this is something we need to prove. And this you can prove again by induction on the length of X, right? And the construction here of M prime. And this is routine. I mean, I'm not going to do this, but this is something you can do. We have seen similar proofs earlier. And then what? So suppose if I want to say, suppose this direction, Lm prime is a subset of Lm. I mean, we can just do this, the other. So once you have the lemma, so assume that you have proved this lemma. So suppose X belongs to Lm prime, then what? Then delta prime star Q0 comma X belongs to F prime, right? Which is, right? Or you can say this is equal to some Q that belongs to F prime. Right? And next what? Yeah. So if this is the case, then Q has to belong to F, right? And next what? Sorry. Uh-huh. So this is, so Q belongs to F. But right. So essentially you see that, so this, I mean, when we are writing in this way, the equivalence class of Q, so that means this equivalence class you are getting by combining several such classes, several such states in this automaton M, right? This class that you get by combining, by merging several such equivalence classes, several such states which are equivalent, which are indistinguishable, right? So that means if this is the case, so they are indistinguishable. So that means there exists some Q prime which belongs to F, correct? And delta star Q0 comma X equal to Q prime belongs to F, correct? So you may not exactly go to this Q. So this is important. This is, I mean, we are referring to this equivalence class as like whether it is Q or Q prime, which are indistinguishable, right? They are equivalents. So it's the same, they are the same, correct? But essentially, when you are going from Q0 to Q, this equivalence class by reading X, that means there exists some Q prime, correct? So there exists some Q prime belonging to this such that Q equal to Q prime and delta star Q0 X equal to Q prime, which belongs to F, correct? So they have to be indistinguishable, okay? Hence, X belongs to Ln. Thus, what do you get? Hence, X belongs to Ln, right? You can also prove the other direction. It's not too difficult, but clear? Any question? Okay, good. And what about the minimality? What about the minimality? it just follows from the indistinguishability relation, right? The set of states that you are getting after the reduced procedure, they exactly correspond to the classes of the indistinguishability relation, right? And you remember that what we saw is something like, given an automaton A, we can consider something like this. And similarly, given, we can also consider this. Right? I mean, so okay. So given an automaton, so given the indistinguishability relation, we could construct this an automaton which is of the form MIL, right? So where the states of this automaton, states of this DFA, of the DFA correspond to the classes of IL, right? And all we are saying is that after the reduced procedure, the DFA that you obtain, is the same as this one. Correct? Right? So after the reduced procedure, suppose you have, like, these are the sets Q prime, right? So it's this M prime, we are calling this Q prime, right? And say Q prime equal to N, right? And if you consider these pairs of states, they are all pairwise distinguishable. These are all pairwise distinguishable. Correct? And we saw that every DFA will require at least this many number of states in order to accept the language, right? And this essentially gives you the fact that the resultant DFA that you get has the minimum possible number of states. Clear? So I think all these ideas are there pretty much in the previous lectures, which we did in fairly detailed way. And you can just try to, I think you just need to sort of revisit them. And once you have those things clear, then it's just a sort of, you'll see that this is nothing new that we are saying here. Okay. It's all because after the reduced procedure, the states that you are getting, so they correspond to the classes of the indistinguishability relation. And since the number of classes of the indistinguishability relation that corresponds to the least number of states of a DFA accepting the same language, you get that the reduced procedure gives you a DFA with the smallest number of states. Okay. Any question? Okay. Good. So now, today we are going to look at an important and an active area of research, I would say. It's called active automata learning. Okay. So this is called active automata learning. So this was proposed by Dana Angluin. Okay. And so often people say Angluin's active automata learning, and this algorithm is also called L-star algorithm. The algorithm is known as L-star algorithm. So what is the idea? The idea is that we would like to learn a DFA. So we would like to learn a DFA. So, and why it is important? Suppose you are given a language L. You are given a language L, Now, it may not be always very easy to construct a DFA corresponding to L. Okay. Now, this algorithm, the L star algorithm, it will construct a DFA through some intermediate but incorrect, through some intermediate DFAs in polynomially many steps. Polynomially many steps. Right? Okay. By, I would say, successively refining them. You have a question? Polynomially many steps, what does it mean? Okay, very good. So polynomially many steps, so I'll say that it is polynomial in the number of states of the minimal DFA accepting the language, and also polynomial in the length of a counter example. So I'll say what is this counter example. Okay, it will be clear in a couple of minutes. So now, how does this thing work? How does the algorithm work? So you can think of this as an interaction between a teacher and a learner. Interaction between a teacher and a learner. Okay. So the learner would ask queries to the teacher. What kind of queries? So one is a membership query. Okay. And the other one is an equivalence query. So what is the idea of the membership query? The membership query is like, you are given a string X, and so the learner asks the teacher whether a string X belongs to the language L or not. And recall that what we are trying to do here, we are trying to construct a DFA corresponding to this language L. And the equivalence query is of the following form, that you have a hypothesis automaton A. What do you have? A hypothesis automaton A, and then you ask the question that does L of A equal to L? So this is the equivalence query that you ask the teacher. The teacher here gives a yes, no answer for the membership query. And here also, the teacher says, so the procedure would terminate. So suppose if it is indeed true, yes, if it is indeed true, so the algorithm terminates. If it is no, then the teacher provides a counter example. Right? So what is A again? A is a hypothesis automaton. So we were saying that we construct this DFA through some intermediate but incorrect DFAs. So this hypothesis automaton can be such an intermediate DFA, and you are successively going to refine that, right? So this is a hypothesis automaton, and the teacher provides a counter example if the hypothesis automaton is not the automaton that you are looking for. And what is a counter example? It's a string. Y, which belongs to L of A minus L union L of A. Clear? So it provides one such counter example, which can either be accepted by the automaton, but that's not there in the language, or it's the other way around. That it's there in the language, but the automaton, that hypothesis automaton doesn't accept it. Okay. And then what the learner would do, the learner would refine. Then you would refine the hypothesis automaton. So we'll see how all this entire process works. The hypothesis automaton. Okay. So this is the very broad goal. Okay. And what you would like to do in order to learn, you want to ensure that you can learn this automaton with small number of queries. Small number of queries. Okay, because you have to learn it. So first of all, the procedure needs to terminate anyway. And secondly, you wouldn't like to learn it with too many queries. You have to be efficient, right? With small number of queries. That's the whole idea. Okay. So now, let's say we go to some more details. Now, in order to do this, there are two sets maintained. Two sets. So one is a set Q, which essentially corresponds to sets of strings. Okay, let me say two sets of strings. One is a set Q, which corresponds to the set of states of the DFA, right? The strings correspond to the set of states of the DFA, right? So we saw these kind of things earlier in the indistinguishability relation, like essentially a set of states can correspond to a set of strings, right? A state can correspond to a set of strings, right? Okay. And you also have, it's called a test set, which is used to distinguish the states in Q. It's called the test set. So what do we have? We have a set of strings. We have two sets of strings, Q and T. What is Q? Q corresponds to the set of states of the DFA that we are going to construct, okay, or the intermediate DFAs, and T is a set of test strings, okay, which is going to check distinguishability among the states of Q. Okay. Now, let's see. So the whole idea is that we will repeatedly, I'm just giving you some intuition. We'll do construct DFAs, make equivalence queries, right? We already spoke about it, and use the counter example, which is provided by the teacher, counter example, to expand Q and T, and then repeat until we find a correct DFA. So this is the whole broad idea. Now, in order to do this, let's define a few notions. So T equivalence. What is T equivalence? Okay. So we would denote it like this. Okay. So two strings u comma v belong to sigma star are t equivalent. Okay, so this is denoted as u is t equivalent to v if for all z belonging to t, we have that uz belongs to L if and only if vz belongs to L. Okay, sometimes we would also say that u and v are indistinguishable with respect to t, or u and v are equivalent with respect to t. Now you note that what is the difference with the indistinguishability relation? So if t is sigma star, right? So this becomes same as IL, the indistinguishability relation IL, if when t is sigma star. Clear? So this t equivalence is with respect to the strings which are there in t, and the indistinguishability relation is with respect to every possible string in sigma star. Okay. Now, what can you say? Suppose if, so just a note here. Note means note that if T1 is a subset of T2, consider two such sets, T1, T2. What can you say about this one? What can you say about this one? Sorry? Which would be a refinement of what? T2 will be a refinement, right? So T1 is refined by T2. Okay, right? And for all T, since T is a subset of sigma star, we have IL refines this. Clear? So IL always refines this. So these are very important observations. We are going to need them at some point of time. So this also gives you that the number of equivalence classes in is at most the number of equivalence classes of IL. Clear? Okay. So now we are going to define two more concepts, or just have two very simple definitions. We say that the set Q is separable with respect to T if the elements of Q are pairwise distinguishable. Distinguishable with respect to T. Okay, or stated otherwise, for all Q comma Q prime such that Q not equal to Q prime okay, we have that it is not the case. That does not hold. Okay. So that means Q is separable. If you consider the strings inside Q, the strings inside Q can be distinguished by some string in T. Is the definition clear? What is the question? So Q is a string. Okay, for now you can think of that Q is a string, Q prime is another string. And the strings, and you say that the whole set capital Q is separable if the two strings can be distinguished by some string in capital T. Q, Q prime, which are not the same, they can be distinguished by some string in capital T. Okay. And this is pairwise distinguishable. Clear? Okay. The definition is okay. Any question? And we say that Q is closed with respect to T if for all Q belonging to this, right? And for all A, let me write it like this in a sentence. If for all Q belonging to this, for all A belonging to sigma, okay, QA is equivalent to Q prime for some Q prime belonging to T. Okay, it is closed. So you consider any string in Q, you take the A, go to Q prime, and the Q prime is T equivalent to QA. Clear? Okay. Now I write a lemma which says that if Q is closed and separable with respect to T, so just take a minute and think like whether these two definitions, if you understand carefully, the definition of separable and closed. So separable is just like they are pairwise distinguishable with respect to T. And closed is like you take any transition, like from Q, you add an A, it's like a transition that you are taking, then you will go to some Q prime, which is also in the same set. Okay. So it is T equivalent with respect to Yeah. So the QA is T. It's clear, the two definitions. If Q is closed and separable with respect to T, then I say delta QA is well defined. Now I'm considering kind of, I have not even defined like what is the delta. I have not given you fully so far the definition of a DFA. But if I try to construct, right? If I try to construct, then what I'm saying is that because of this closure, the closure gives you that if I read an A, there exists such a Q prime where I can go to, because this QA is equivalent, T equivalent to this thing. So I can go to this Q prime. And further, this is unique. Further, this Q prime is unique. You cannot have two possible such things. Why? Why? Because of the separability, right? Because I cannot have a Q prime which is T equivalent to QA, and I cannot have another Q double prime which is T equivalent to QA, because this is an equivalence relation, then these two have to be equivalent, correct? So there is a unique such Q prime which is T equivalent to QA. So this transition relation, if you consider a DFA, this is well defined. Okay. So this lemma gives rise to this leads us to the construction of our hypothesis DFA. This leads us to the construction of our hypothesis DFA H, which is of the form Q sigma delta epsilon. Okay, initial state is epsilon, because what are these Qs? So these are sets of strings. This is a set of strings. Q is a set of strings, and epsilon is the initial state. And this is my F. What is F? F is the set of Q belonging to Q such that Q belongs to L. So my capital Q, it has some strings. It's a set of strings. Correct? So I will consider those strings which are in L, and I'll call them final. The only thing that you would need here is that, which I have not so far mentioned, is that in order to construct this hypothesis DFA, since the set of states is this capital Q, this Q has to be finite. So now we'll consider that Q and T are finite. So we'll have this assumption for now, and we'll see in a while that why this is good enough to have this assumption. My Q and T both are finite. Okay. So we talked about separability, we talked about closed, and then we say that if Q is closed with respect to this capital T, then you can indeed construct such a hypothesis DFA. Okay, good. Now let's write an important lemma, which I have already written down. So suppose you were given a hypothesis DFA H. where Q is closed with respect to T. Okay. And suppose with this hypothesis DFA, what do you do with the hypothesis DFA? You ask the learner, asks the teacher whether this is the DFA I'm looking for. If it is indeed the case, then you get your DFA. If it is yes, the procedure ends and you have a DFA with you. If it is not the case, then what does the teacher do? The teacher provides you a counter example. Suppose this is how a counter example looks like. It is a string of length, let's say M, string of length M. Now, what we say is that if there is a counter example like this, then we can find strings Q and T such that this is a new string which does not belong to this capital Q, and this is a new string T which does not belong to this capital T, and Q union Q is separable with respect to T union T. Okay. So if it was closed and you have a counter example, then we can find strings Q and T such that Q union Q is separable with respect to T union T. Right? So which means, what does again separable mean? So all the strings here, they are pairwise distinguishable with respect to the strings in T union T. So you can add one string Q to this set Q and one string T to your test set if Q is closed with respect to T. Then you can do that. Okay. So why is it the case? Okay. So it's not that obvious. So let's try to prove this. Okay. So suppose you have delta star. Okay. Your initial state Q0, which is the same as epsilon, right? And I say that W1 to Wi, let me call this Qi. Starting from this, if you read this prefix, if you read the prefix of the string, I call this Qi. And I say that Qi is correct. Qi is correct if Qi Wi plus 1 to Wm belongs to L, W1 to Wm belongs to L. So what is this? So I have a DFA. I have this hypothesis DFA. Hypothesis DFA H, right? Now in this hypothesis DFA H, if I read such a prefix from Q0, I will reach some state Qi. Now Qi is a string. Qi is a string. I am appending the suffix Qi Wi plus 1 to Wm. And I get a string here by appending this suffix to Qi. Now I am saying that this Qi, the state Qi or the string Qi is correct if by appending this suffix to Qi belongs to L, if and only if the whole string, that is the W1 to Wm, this whole string also belongs to L. There is a clear? Your DFA has a set of states, but the set of states, the states themselves are strings. Okay. And you reach here, and then I'm saying it is correct if this is the case. By appending the suffix, if this belongs to L, then this should also belong to L. Now you see that your initial state, which is epsilon, is correct. Clear? Initial state epsilon is correct because epsilon dot w1 to wm is the same as w1, right? Is it okay? Because epsilon dot, so when I say qi this, it's like a concatenation. Epsilon dot w1 to wm belongs to L if and only if w1 to wm belongs to L. So your initial state is correct, epsilon, right? What about the final state? Suppose the final state is qm. The final state is qm. Qm is incorrect. Why? Why? Because W is a counter example. W is a counter example, right? Which means that suppose W is in the language. Suppose W is in the language, right? So I'm saying that this, suppose W1 to WM, it's a counter example. If this is in the language, then your hypothesis automaton should not accept it, right? So it means that QM, right, dot, what is the suffix? The epsilon is the suffix, nothing is left. So that means QM does not belong to L, correct? Because it's a counter example, or it could be the other way around, like QM belongs to L, but W1 to WM does not belong to L, right? So epsilon is correct, QM is incorrect, correct? Okay. Hence, we can say, hence, there exists some I such that I less than M such that Qi is correct, but Qi plus 1 is incorrect. There should exist such an I, right? There should exist such an I in which Qi is correct, but Qi plus 1 is incorrect. Okay. Right? And now, what we would like to do is, okay, so if Qi is correct, so that means Qi, and then you are reading Wi plus 1, and you have Qi plus 1, right? So you have Qi is correct. So you have right, and here you have okay. So what is happening, or maybe let me just change the index a bit so that there exists, let's say Qi minus 1 is correct, and I call Qi is incorrect. So Qi minus 1 Wi and Qi, okay, and here it is Wi plus 1 to W. So what can you say from here? So Qi minus 1 Wi and Qi, these can be distinguished so these two strings can be distinguished by the string this one, right? Okay, is it clear? So what is happening if this is correct and Qi is incorrect? So let's again understand, like if this is correct, but this is incorrect. So what does it mean to say this is correct? So, and this is incorrect. So what does it mean? It means that Qi minus 1 Wi to Wm, it's not equivalent to Qi W I plus 1 to Wm. Right? Is it clear? Because see, this one is correct. This one is correct. Right? So which means that if this belongs to, okay, so I think, let me, okay, so if this is correct, so that means this is equivalent to saying W belongs to L. So where W is this, where W is this, right? If this is correct, then this is true. And whereas if this is incorrect, the right side, then this means W not in L, correct? Because this is incorrect, right? We said there exists an I such that Q minus I, this is incorrect, this is correct, but this is incorrect. Correct. So if that is the case, so if this is incorrect, so it means that this belongs to L. If this is the case, then W cannot belong to L because it is incorrect. So this is the definition of the, what is the definition of the correctness? So it's this. So if this is belongs to L, then W belongs to L. So what is confusing you? The definition of incorrectness? Then so again, epsilon is correct, it is clear. QM is incorrect, this is clear. If this is the case, this is the case, then there exists some I such that Q I minus 1 is correct, but Qi is incorrect. This is okay. Okay. Now, if this happens, so what does it mean to say that this is correct? That means that Qi minus 1, this belongs to L, is equivalent to W belongs to L. This belongs to L if and only if W belongs to L, from the definition of correctness. This is incorrect. What does it mean? This means that Qi and the suffix belongs to L if and only if W does not belong to L. Right? The definition of incorrect, what does it say? So are you getting confused here? So if I would have said that this is the case, then, so just look at this part. Then Qi is correct. If this is the case, then Qi is correct. Huh? Is it okay now? So now I'm saying that, so the definition of correctness is, if this belongs to L, then this has to belong to L. But since Qi is incorrect, so that means this is the case. Since Qi is incorrect. Are you having a trouble here? It's okay? Okay. So now, if this is the thing, then this was correct, this is incorrect. So if this belongs to L, then this cannot belong to L, and vice versa. Okay? Or not really? Because we are saying this is correct, this is incorrect. This is correct, this is incorrect. Now suppose if this is correct, so suppose this belongs to L and this is correct. So then the suffix starting from here, if this is correct, then this cannot belong to L, right? Okay, maybe my notations are confusing you. It's not that difficult. So all I'm trying to say, okay, so Q minus I minus 1 is correct. Suppose this is the case. Suppose this is the case. Then Qi Wi plus 1 Wm does not belong to L. Because since Qi is incorrect, right? Because if this is correct, then W has to belong to L since this is correct, Qi minus 1 is correct. And since this belongs to L, then W has to belong to L. Now, since W has to belong to L, since this is incorrect, since Qi is incorrect, this cannot belong to L. Otherwise, if this had been in L, then Qi would have been correct, right? So this cannot belong to L. Qi followed by this suffix cannot belong to L, correct? So again, so what do we get? Or it could be vice versa. So we just said, so we said the following: Qi minus 1 Wi to Wm belongs to L. Qi Wi plus 1 to Wm does not belong to L, or it could be the other way around also, right? This correctness, incorrectness can give you the other way around also, that Qi minus 1 Wi to Wm does not belong to L. Qi Wi plus 1 to Wm belongs to L, right? One of the two cases. One of the two cases, right? Depending on the counter example, whether the counter example belongs to L or not. If the counter example, if W belongs to L, here if W does not belong to L. These are the two cases, counter example, right? And this is based on Qi minus 1 is correct. So this is correct. In both the cases, Qi minus 1 is correct, whereas Qi is incorrect, right? You get this, either this or this, either this or this, one of the two. Clear? So what does it mean? It means that Qi minus 1 Wi and Qi are distinguished by Wi plus 1 to Wm, this string. Okay, these two are distinguished by this string. Now, if this is the case, what do I add to Q? Now you consider Q prime equal to Q union qi minus 1 wi. So qi was already there. Qi minus 1 was already there, right? And I'm adding this new string, qi minus 1 wi, and I'm adding to t prime t union wi plus 1 to wm. Okay. Now, what did the theorem's lemma say? It said that if I now have this is separable with respect to this. Correct? So why this new string is separable with respect to this? So note that qi minus 1 wi was t equivalent to qi. Qi minus 1 wi was t equivalent to qi. Right? It was closed because of the closure. Since q is closed with respect to t, is it okay? But qi minus 1 wi is not, but qi minus 1 wi is not t union this new string. Equivalent to qi. Okay? Right? And hence this string, so this was equivalent to this. So that means this is not equivalent to any other string qj in q. qi minus 1 wi is not equivalent to anything else in q, right? And it is not equivalent to qi anymore once you add this new test string. Hence, q union qi minus 1 wi is separable with respect to t union wi plus 1 to wm. So I'm going to share a note which was written by Malhar when he did this course. You know Malhar, right? You haven't met him yet, like he's a student. So, and he wrote a very beautiful note, like, so he made this presentation and he was also auditing just like you. And he made the presentation of this. So at that time, I did not teach this myself, but it was um, one of the topics which the students, like the student, I mean Malhar, in for this topic he presented, and you can just go through this, and I'm just following his notes. Okay, right? So this lemma is clear, right? So if it is closed, see, the closure property is very much required, and since this is closed, you have that this is separable with respect to this. Okay, so this is this, and now we'll add one more lemma, and we'll just write the final algorithm, and maybe in the next lecture we'll go through an example. Okay, so now, so this is one lemma, right? So if there is a counter example that you get that your hypothesis automaton is not the actual automaton, then you can indeed add a new string to the set Q as well as a new test string to the set T. Now we'll write another lemma which says that if Q is separable T, it is possible to add finitely many strings to Q, resulting in a set Q prime that is closed and separable with respect to T. Okay, so suppose Q is not closed. Q is not closed with respect to T. Then what happens? Then by the definition of closure, there exists a Q and there exists some A such that QA is not T equivalent to Q prime for all Q prime belonging to Q. Okay. So if this is the case, then Q union QA is also separable with respect to T. If that is the case, then Q union QA is also separable with respect to T. And we can repeat this process. We can repeat this process until Q is closed. Okay, and all we need to show is that we need to repeat this process, show that only for finitely many times. Okay. So one thing, is it clear that number of classes is it clear? Why? Suppose this is not the case. Then there will be two QIs and QJs which are in the same class, right? And then it contradicts the property of separability. Since they're separable, this holds true, right? And what do we know? This is less than equal to number of classes in IL, the indistinguishability relation, right? Since the language L is regular, finite, since L is regular. Correct? Right? If you're adding this, if you're adding this, right? You can at most get the number of classes in this T equivalence relation, and that is finite. right? So you can add finitely many strings to queue, right? Until you get the closure property. Okay. Clear? And we know that this is anyway closed, right? I mean, if you consider the strings here, like the partitions here, this is anyway closed, the corresponding to this thing. It's always, it's always closed, right? So you cannot continue to do this and get something which is not closed. Okay, so eventually you will get something which is closed, and you can do this only finitely many times. You need to add new strings to queue. Okay. 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 So now I will just give you the intuition, and then we'll look at this algorithm, and then we'll end, and in the next lecture we'll look at an example. So what does the L star algorithm do? So we looked at two things. One is an equivalence query. If you do the equivalence query, and if it is not that automaton that you are looking for, the teacher gives the learner a counter example. Based on that, you can add a string, you can add a test, you can add a string to set Q, you can add a test string to set T, and then by this lemma, you can further add new states to the set Q until the set becomes closed and separable. I mean, it is already separable until it becomes closed. Okay. You can do this, and all you need to do this is finitely many times, and you get a new DFA. You get a new DFA, and again you ask the equivalence query, right? So where is the membership query used? Where is the membership query used? So you see here in this proof, we are trying to find such an I, which is qi minus 1 is correct, but qi is incorrect. And how do we do this? By appending the suffix and checking whether this is in L. When we are doing all these checks, then we are using the membership query. Okay. Right. And also when in this lemma, when we are checking that if QA is T equivalent to any Q prime. So how would you check this if QA is T equivalent to any Q prime? This is also a membership query, right? This T equivalence is defined based on the membership to L. Correct? So you will take, so here, how do you do this? Sorry. How are you going to check this? Essentially, QA T, whether it belongs to L, and Q prime T belongs to L, you check this for all T belonging to T. You are doing the membership query in these phases. Okay. So what is the broad idea? So you are using this, using equivalence query, and then perform the closure operation, right? And in this process, you expand the set Q and set T. You are doing this until, right? Until the number of strings in Q becomes equal to the number of equivalence classes in IL. Okay, so at this point, what happens? You get that Q is the set of equivalence classes of IL and the hypothesis DFA is the minimal DFA accepting L. Right? So this is the broad algorithm. So I just gave you the intuition. So this is the broad algorithm. So initially your Q is the string epsilon. It's not the empty set. It has the empty string. T also has this. Right? Now you add elements to Q such that Q is separable and closed. So initially this is separable with respect to T because you just have epsilon. Right? You just have one state. You just have one string in Q, correct? So it is like you don't have anything else in order to kind of which you would like to distinguish, correct? So this is separable. And now you ask the question that you have a hypothesis automaton. So initial automaton can look like you have the epsilon, you have the sigma like this, and your T is like this. So already this is separable, right? And now you ask the question that well, it may, right? Yeah. So you ask so you want to make it separable and closed, and if it is already the case, then you compute the hypothesis automaton. You compute the hypothesis automaton you get this by doing the closure and this thing. You get a hypothesis automaton, which we'll see through an example, and you ask the equivalence query. Now the teacher answers yes, then you terminate, and you already have the automaton. If the answer is no, then you apply that lemma, the first lemma where we saw that you can indeed get a new string and a new test string, and you obtain your new Q prime T prime by adding those strings to Q and T respectively. And then you go to step 2 again. Like, so you make Q prime closed with respect to T prime, you make Q prime closed, and the second lemma says that you can do it in finitely many steps, and then you get a new automaton. You again ask the equivalence query, and you keep repeating this until you get the teacher says yes when you have the DFA. Okay, clear? So we'll just end here, but what we would suggest is that this example, the language L, the third character from the end is a 1. Third character from the end is a 1. Can you construct the DFA using this algorithm, the Elster algorithm. Clear? Can you construct the DFA using the Elster algorithm? So this is the homework, and we'll discuss this in the next lecture, which is on Thursday. Okay, so let's then end the class here today. Any question? Do you have any question? Okay, so if there is no more question, then let's end today, and we are going to meet on Thursday.